Welcome to PHDwin Week 2024. It's an honor to be invited back to this distinguished conference. I would like to extend my gratitude to the TRC team for organizing such a valuable event. I also want to thank all of you for joining from various parts of the world. Your presence and participation are truly appreciated. Allow me to introduce myself. My name is Marylena Garcia. I'm a reservoir engineer with more than 25 years of experience. I've been with Ryder Scott for 14 years, initially dedicated to evaluation of oil and gas properties for reserves certifications and audits. However, lately I've been doing more sustainability work related to greenhouse gas evaluations, including carbon capture and sequestration. I also ensure compliance with environmental agencies, especially those that set the guidelines for the evaluation, just like the EPA here in the United States. Here at Ryder Scott, we offer comprehensive services across the entire value chain. Our expertise expands from upstream, midstream, and also a sustainability division. In the upstream department, Ryder Scott has a rich history of providing top-tier, excellent technical expertise in the upstream sector. We have a team of seasoned professionals, and they excel in reservoir evaluation, reserves estimation, and also resource simulation. In the midstream department, we also have trusted advisors for energy infrastructure projects, and they specialize in pipelines and facilities engineers, ensuring the efficient and safe transportation of the energy resources. Finally, in the sustainability division, which I lead, we use our extensive experience and a unwavering commitment to excellence to offer greenhouse gas evaluation services, compliance with regulatory standards, also emission reduction and facility recommendation and strategies, and as I said before, carbon capture and utilization storage, among other services. We have a strong client base around the world. We've been in service for 87 years, 87 remarkable years, should I say, and we have the privilege of serving hundreds of companies around the world. Our journey has been one of growth, innovation, and lasting partnerships, and we look forward to continue with this legacy of excellence. Today's presentation is going to be about the integration of carbon capture, utilization, and sequestration, CCUS, in the oil and gas industry. I'm very excited about this particular presentation because we'll explore how to use 45Q tax credits to help companies reduce the greenhouse gas emissions while enhancing operational efficiency and generating financial incentives, whether it's through CO2 Enhanced Oil Recovery, EOR, acid injection, or dedicated geological storage. We'll learn how to unlock these revenues and drive sustainability. Today, I'm going to cover this agenda. I'll start with an introduction, a brief understanding of carbon capture and his role in the oil industry, and then we'll dive into the subject, which is the strategic utilization of the tax credits, either for CO2, EOR, or acid gas injection. We also look into some regulatory compliances consideration regarding the permitting of these two types of processes and specific classification of wells. And then we're going to go on an overview of the tax credits. And I'll finalize with some remarks. This image is a stacked area chart showing the global CO2 reduction per year from 2019 to 2070 using various technological and energy solutions. The chart shows the contribution of different strategies to reduce carbon emissions, and they are expressed in gigatons. This figure right here was put together by the International Energy Agency, and the target for carbon capture and storage by 2050 is 7.6 gigatons of carbon dioxide stored annually. And this is a significant increase compared to the current level of 0.0 gigatons captured and stored annually. With an intent to reduce greenhouse gas emissions, oil and gas companies are exploring different ways to become carbon neutral in the next 20 and 30 years. To achieve this target, carbon capture and sequestration plays a vital role. With the help of petroleum engineering and geoscience skills, companies need to leverage existing assets and technologies to establish a successful low-carbon venture technology. As part of our commitment with innovation in the field of carbon capture, Ryder Scott uses the Blue CCS platform. It's an advanced AI power tool that provides an interactive access to information on both active and announced CCUS storage sites around the world. This platform integrates publicly available information from a wide array of sources, offering detailed emission sources at pipeline infrastructure, and we use it to help our clients make informed decisions about their CCUS projects. The United States has emerged as a global leader on carbon capture and storage deployment, driven by its strong policy framework, tax incentives like the 45Q, and also an advancement in carbon capture technologies. Here are several key reasons why United States are at the forefront in carbon capture development. First of all, we have a strong policy support, financial incentives. We have carbon capture and sequestration projects and facilities. We are leaders in EOR. And also, as you can see in this picture, we have the geological advantage. We have sufficient storage for enough of the emissions that we produce in the country. This image shows a detailed map of the US taken from a Blue CCS platform, highlighting the various aspects of carbon capture utilization, the infrastructure across the United States. It displayed the location of the CO2 pipelines, both proposed and operational, and also the fossil fuel operations and manufacturing sites, power plants, etc. Maybe some of you are already familiar with carbon capture and storage, but this is just a quick diagram to illustrate the process of carbon capture utilization and storage. It begins with a CO2 source, which could be industrial facility of a power plant where carbon dioxide emissions are generated. These emissions are then captured and then compressed and transported via most likely a pipeline to either of two places. They could be either be injected permanently on a geological storage, or they can be utilized where they can be used for EOR purposes, also via feedstock for other products. In this presentation, we're going to be talking about these two, geological storage and also EOR. To perform the injection of the CO2 in the ground, in the United States, we have different type of classes of well. These are regulated by the EPA under the Underground Injection Control Program. It consists of 6 classes of wells, of injection wells. Each well is based on the type and depth of injection activity and the potential for that injection activity to result in an enlargement on the USW. This image represents a classification of different types of injection wells under the U.S. Environmental Protection Agency and the Underground Injection Control Program. And they are used for various purposes, including disposal, enhanced oil recovery, and also carbon storage. In today's presentation, we're going to be focusing on Class 2 wells, which are wells dedicated to the injection of fluids associated with oil and natural gas production, and also Class 6, which are also called dedicated CO2 injection, and they are used for injection of CO2 and long-term storage on geological formations. So one is for EOR and waste, and the other one is for dedicated storage. So in this slide, aiming to compare the two type of wells, class 6 versus class 2 wells, in terms of their permitting requirements. They are both inject CO2. They are both aiming to fulfill the same functions. However, the permitting between the two is different. The class 6 application, that's the one that is for dedicated CO2 storage, is regulated in most of the country by the EPA, except for Louisiana, Wyoming, and North Dakota, because they have primacy. That means those states have authority to grant the permission. This process, when it's conducted via EPA, is a lengthy and a very iterative application process. It has a very also strict and extensive site characterization requirements, including acquisition of extensive data, core drilling, seismic, etc., even reservoir simulation. It also requires a pre-operational testing plan, well construction and stimulation plan, operating plan, area review, which is the area where the monitoring of the CO2 plume concentrates, and also the corrective actions, comprehensive monitoring, and also a well plugging plan, emergency and remedial response plans, and also a site closure program. And the operator or the owner of the project has to demonstrate financial assurance and responsibility. In contrast, the class 2 wells is presented here as an alternative over class 6. The class 2 wells is regulated by the states. That means that the own states does the approval of the permitting. Therefore, the timing for the permitting is quicker, and also the application process is less stringent. It requires well construction, well integrity, of course, monitoring and reporting, well closure, and post-closure care. The advantage, in my opinion, of this well is this type of wells is the one used for the EOR in the entire United States. And the CO2 injection has been carried out with this type of well for decades for fluids associated with oil and gas. So it provides also a faster path to injection and monetization through the tax credits, because the application process is just more faster. It's just faster. So which one is better? So they're both eligible for tax credit. However, the class 6 application has a higher tax credit amount, so it's more economically attractive from that regard, and we'll discuss tax credit in a little bit. The permitting frame would take more than 2 years. Also, it's very capital extensive in both cost and scope. It requires the drilling of the well, acquisition of seismic, a very comprehensive geologic site characterization, and it's very demanding in terms of the scope, and also the level of characterization and depth of the evaluation that had to be done to characterize the entire injection site, in the injection zone plus the underground aquifers. Also, the bonding obligation remained 50 years after the P&A for most states. And if you compare that to the class 2 wells application permit, this is also eligible for for tax credit, either for CO2 EOR and also for acid gas injection, which is not very common, but it's possible. And also, if it's EOR, on top of the tax credit, it has the tertiary financial benefit. Also, the existing class 2 wells operators are really familiar with the regulatory environment and the operation, because they're, as I said, they have done this type of wells for decades. The permitting time frame is less than a year. As I said, is done within the state, especially in Texas, in other states as well. And the bonding requirements are lifted after the P&A in comparison to the class 6, where they remain 50 years after the well is P&A. However, these class 2 wells is not an option for those industries that are not oil and gas. So you compare this asymmetry between the benefits and the liabilities between the class 6 and the class 2 well, creates a large hurdle for many projects to overcome the class 6. So that's why class 2 presents itself as an opportunity for oil and gas companies that are maybe not so interested in conducting a full-blown carbon capture project per se, but maybe want to leverage on their knowledge on CO2 EOR and perhaps the presence of acid gas in their production stream, and they can leverage those conditions in their operations and use the tax credit to receive that incentive, and at the same time maximize and optimize their operations. So we have the class 2 well for sequestration. This is what we're proposing. This is the message of this slide. Let's see the class 2 wells with the eyes of sequestration instead of only the class 6 wells. Especially because of the complexities around the application with the class 6. So the class 2 wells, as I said, are used for CO2 EOR or also enhanced gas recovery. So the purpose of the wells is very well known for all of us, is the injection of CO2 to increase oil and gas extractions. It's a popular production mechanism, the tertiary recovery that is used worldwide and is very well known here in the United States. Acid gas injection is less common, but it's also possible. Is the disposal of acidic gas could be CO2 operation, the CO2 remain underground in the reservoir, and that's the mechanism from which it's trapped, and it remains in the reservoir and thereby is preventing from entering the atmosphere. The EOR is not a new process to us. It's been proven for more than 50 years. We have a lot of experience conducting this type of the operations. And some of the portions, as I say, some of the portions of the CO2 would remain trapped in the pore space within the reservoir, essentially becoming permanently sequestered. The CO2 mixed with the oil is eventually produced, but this produced CO2 is separated and then is injected back again. And that reinjection process is shown here in this closed loop system. The CO2 operation is essentially a closed loop. The CO2 is injected and is trapped within the reservoir, and the CO2 is also produced with the oil, but is recycled in the surface, separated and reinjected back into the reservoir, with increasing portion of the reinjected CO2 getting trapped during the process all over the life of the EOR. At the end of the flood, Essentially, all purchased CO2 is stored within the reservoir when the operator closes the field. The diagram on the right depicts a simplified schematic of the process flow for CO2 EOR as depicted on the ISO 27914. And it shows the CO2 purchases of CO2 supplies enter the EOR complex from a pipeline delivery system and is received through custody transfer meter. And then the purchased CO2 plus the recycled CO2 are sent through the CO2 trunk lines to injection manifolds. So each well has a flow meter and used to measure the injection rate of CO2 and also water for those ER processes that use WAG. Then every CO2 recovery plant is different, depending on the flood maturity and the size of the project. However, there's always a balance between the fresh CO2 or the purchased CO2 and the recycled one. In mature floods, it could be 47-53% between the recycled and the fresh CO2. But this ratio is expected to change over time, and the percentage of the CO2, the percentage of the recycled CO2 will increase, and the purchase of fresh CO2 will taper off. So as CO2 is injected and moves through the reservoir, a mixture of oil, water, and gas flows through the production wells. The production is sent to the production facility, and the separation is performed there. So the liquids are separated, cell oil, and the water is sent to different lines for disposal and sale, and the gas is sent to the plant, where is also separated from the cell gas, and the CO2-rich stream is recycled and is injected again. And this process is repeated all over again. So CO2 storage using CO2 EOR operations has some advantages and also some challenges. On the pro side, we already know the geological characteristic of the field. We have an improved geological understanding because we've been working on this field for years, and we know it. We believe we have a deep knowledge of the characteristics, geological and engineering of the fields. Also, we also know the injectivity and their capacity. The containment is demonstrable because if the reservoir was able to contain the oil for a period of millions of years, so it can also contain the CO2. So the seal is demonstrated. It doesn't need to be proved, like in the case of saline aquifers. We have existing infrastructure in place. We have roads, we have well paths, etc. We have a routine for pressure management. There's a culture in the field for this type of surveillance activities, and also the MRV or the monitoring verification is easier because of the existence of the surveillance processes. The challenges is the existence of legacy wells, because legacy wells or existing wells may be a possibility of leakage of the CO2 within the reservoir. Also, there's a possibility of some geomechanical damage from the previous, from the CO2 injection for the exploitation of the oil. There could be a risk of CO2 movement outside the CO2 complex, the CO2 EOR complex. And transfer the CO2 between the field is a common practice and within the operation, but that can become an issue when we're talking about storage, because we don't want the CO2 that's been stored within a specific CO2 complex to get out of that area and move to another field. We want every molecule of CO2 that's been stored to remain in that particular area for accounting purposes. And also the in situ CO2, that CO2 that was in the reservoir from day one, if that exists, that needs to be accounted for or needs to be estimated before Otherwise, will be a problem with the accounting of the CO2 that's being stored. The CO2 that is being injected on a CO2 EOR, as I said, cannot come from natural occurring underground deposit of CO2 if the operator wants to apply for the tax credit, which is what we're talking about here. So it can really use any type of CO2, but however, if they want to apply or be eligible for the 45Q tax credit or any incentive, it has to be gas coming from industrial sources. And that CO2 should be captured as a byproduct of fossil fuel, combustion gasification, or other industrial processes from power plants, cement plants, ethanol plants, ammonia plants, etc. But that CO2 has to come from industrial sources. And according to the section 45Q, it defined the qualified carbon outside as capture from an industrial source by carbon capture equipment, would otherwise be released to the atmosphere. So to be eligible for the credit, it has to be from industrial source. It cannot be from underground deposits. Whether we like it or not, we have plenty of industrial source CO2 to go around. This is a picture also taken from our Blue CCS platform, showing as of 2023 the annual global emissions from industrially sourced CO2 at 37 gigatons per year. So it's an incredible amount. These numbers goes to prove the amount of CO2 that is available for injection. At the same time, as I shown in the previous plot, we have enough storage capacity or storable volumes, storable quantities in our geological deposits worldwide to accommodate all these or inject and store all this CO2 that is currently being emitted. So since the CO2 45Q is performance-based, it really the CO2 needs to be quantified in order to claim any type of credit. So it can be, in some cases, how much CO2 is being injected in CO2 EOR operation can be quantified based on all field experience. However, the CO2, the amount stored is specific for each field. In the United States, this amount has to be validated or certified by an independent, by a third party. So if we're following the ISO standards, the ISO 27916 define a workflow for the estimation of the CO2 stored, which is the input minus the losses in the EOR complex, as is shown there in this box. There are also other ways to calculate how much CO2 is being stored as a result of the EOR process, and that's based on a CO2 utilization factors, which is the equation B right here. And it uses a CO2 utilization factor based on the experience. So here I'm showing some numbers that are analogs, are found in some publications. So we have the mid, the maximum, and the minimum value. So average is around 0.5 tons per barrel. So use that metric and then multiply it by the original oil in place and recovery factor. You can have an estimation of how much CO2 has been stored in your reservoir. There are other papers like this one published by Dr. Larry Lake and others, where it shows a summary of the cumulative CO2 retained as a function of the hydrocarbon pore volume of CO2 injected for a large data set of CO2 EORs. The red curve is the mean, and the black ones, the black curves are the 1 and 2 standard deviations around the mean, and the solid and dash black, and the dash black corresponds to the limiting case of zero retention. So, for example, all the CO2 injected is produced. So for the average curve with the red line, the flattening occurs at retention of 40%, which is 0.4, 40% of the hydrocarbon per volume. And the residual oil saturation to water after water flood in hydrocarbon reservoir is around 0.3 or 0.4, which is a rough, which is in rough agreement with these results. And the plot on the right-hand side suggests that the ultimate CO2 is correlated with that same residual oil saturation. So in the plot on the right side shows that the amount of CO2 retained as a function of CO2 injected. And this behavior is more directly relevant to carbon capture and sequestration operation. Because it's not the x-axis is not using the water, there's a disparity between the two axes, and that's why we cannot see the deflection or the flattening trend that we see on the plot on the left. However, the CO2 retention is around the same number, 0.4. So after we have a successful CO2 EUR, at some point that can be transitioned into geological storage or dedicated CO2 for a dedicated CO2 injection. So that it can be done according to the regulation, and a class 2 well can also transition or be repermitted into a class 6 well. So CO2 EUR may end when the oil field reaches the economic limit, and after the end of the injection, a considerable amount of CO2, will be intrinsically or inherently stored. After that, the field can become a dedicated geological storage CCS site. So now I'm not talking about EOR, talking about what's coming after the end of the EOR, when the CO2 injection and all operations stops. So those EOR wells must be transitioned to class 6, and of course have to follow all the process that I explained earlier and all the permitting through EPA. And all the CO2 must be tracked and accounted for. The transition from class 2 to class 6 is not a trivial process. It requires long-term planning, and that becomes very critical, because it is something that it takes so much time to do the class 6 application, obtain the permit, that it really had to be thought and planned away in advance. So the EOR fields are regulated by the states, but however, if we want to transition to a class 6, then on the state where you have your field doesn't have primacy, then it had to be regulated at federal level, which it can get things complicated. So following a determination or that the conversion had to be done, it has to meet all class 6 requirements. And then it starts the challenges. We have higher liabilities, different and more complex monitoring requirements, and also regulation for well abandonment. Some things to think about: that the field might be pressurized after a long time of injecting CO2 and keeping that pressure above minimum visibility pressure. So that field might be pressurized, so something to keep in mind. And also you have legacy wells that may have integrity issues because they've been injecting for a long time. So that's the challenge. The transition from class 6 from class 2 to class 6 is possible, but it comes with all these challenges. So the other alternative to CO2 EOR that I would like to present to you today, that when we talk about the integration of CCUS into the oil and gas industry, is the acid gas injection. To me, this is an excellent CO2 storage opportunity. CO2 EOR is great, and this one, acid gas injection, is just as good. The definition is the injection of waste gases like CO2 and H2S into geological formation, creating a safe and effective disposal. The acid acidic gas comes from the production of oil and gas for oil and gas operation. So basically, this gas has to be separated from the natural gas, and in many cases, or before the existing regulation, used to be emitted, but it also can be injected in geological formations to, better and lower carbon footprint, and also it qualifies for a tax credit. So beyond reducing the greenhouse gas emissions, it offers an efficient solution for managing the gas and at the same time optimizing field production and sustainable operations. Acid gas injection amplifies the effectiveness of emission reduction goals, showcasing commitment to responsible energy production practices. Acid gas injection, I think, is an important step towards large-scale capture and geological storage. And we cannot forget that this is a critical step, because to meet natural gas transportation and also market specification, the hydrogen sulfide and the carbon dioxide and other gas impurities, which are known as acid gas, must be removed from the natural gas. Otherwise, that gas cannot make it to the pipeline. So in the past, these gases were removed from the gas stream, but flared to the atmosphere. So acid gas injection has the beauty of it is like that gas is now injected into geological formations and also becomes a CO2 storage opportunity. So the target for acid gas injection are more or less the same, the ones we use for geological or dedicated CO2 storage, or normal CO2 sequestration. It could be depleted oil and gas fields. It could be depleted salt caverns. It could be saline aquifers. Saline aquifers is most common, but also oil and gas field. But saline aquifers is very attractive option. It has key similarities between acid gas injection and CO2 sequestration, because the goal is the long-term containment of the geological reservoir. So if you compare it to CO2 EOR, the goal of EOR is produce oil, right? And the CO2 is stored almost incidentally. With acid gas injection, the CO2 storage is intentional. So that's kind of the difference between the two. And also carbon capture and sequestration or storage, acid gas injection acid gas injection shares some significant similarities in that regard. However, the magnitude of the operations is different, and also the gas composition is different. Gas injection is a less less scale. For example, for CO2 EOR and also for dedicated CO2 injection for CCS, we're talking about millions of 1, 2, 3, 7 million of tons injected per year. For acid gas injection, we're talking about 200 to 450, maybe 500 kilotons per year. So it's a huge difference in terms of the magnitude of the amount being stored. And also the gas composition is different. Remember, we're talking about here gases that are not totally pure, so I may have some H2S and also other components that are not so pure CO2. So again, for acid gas injection, most of the producing states have primacy over class 2, because class 2 is the class of well that is used for acid gas injection. So it wouldn't be a problem for the permitting, and also have the potential revenue source from 45Q. And later on, if the environmental agency require, these wells can be converted to class 6 if they're needed to sequester CO2 from non-oil field sources. In regards of the acid gas injection permitted requirements. In the US, the operations are conducted following the indication of the guidelines of the EPA under the Underground Injection Control, UIC, the program regulations. This type of water classifies as class 2, as I said, associated with oil and gas production. And some of the requirements are the permitting, the operating procedure, monitoring, mechanical integrity testing, and closure. Very, very similar as the EOR that we reviewed earlier. Also, the CO2 must be from oil field or gas field waste. It cannot be from natural sources, otherwise it wouldn't qualify. And also the gas stream has to have less than 90% CO2. Also, there's a minimum, depending on the state, there will be a range between minimum and maximum injectivity constraint that will depend on the states. And also, it will need an amine system to sweeten the CO2 and to extract the CO2 and purify it to certain level of purity, say 98, 99 purity. And it has to have compliance with that credit and the common requirements. It have to have a class 2 permit. It had to have the MRV and MMV permits, pipelines, and also air permits. Okay, so let's talk about the 45Q carbon sequestration credits. This is exclusive for carbon capture projects that occur within the United States. And the 45Q, which is the tax, that's the number of the tax code. Tax code 45Q serves a crucial mechanism for advancing the transition to a low carbon economy. Because as you can see, CO2 EOR may have financial benefits from the tertiary oil that is being produced, but a dedicated CO2 storage or acid gas injection doesn't have that extra income. So the 45Q incentive are really significant and crucial to allow the implementation and the financing of these type of projects. The 45Q is the tax credit is a dollar for dollar offset to U.S. federal income tax liability. The amount of the credit available is based upon the amount of carbon dioxide that is stored and is used as an injection for oil and gas recovery or utilized for other purposes. It's linked to the installation and use of carbon capture equipment on industrial sources or facilities that would directly remove the CO2 from the atmosphere. The tax credit goes directly to the entity doing the capture, I mean, the owner of the capture facility, but they can be transferred to other entity involved in the utilization of the storage. So the tax credit varies based on the carbon outside method of the sequestration or utilization. For geological storage, if the capture is a point source, that is in the plant, is $85 for geological storage. If it's used direct capture, then the tax credit goes up to $180. For CO2 utilization and for CO2 EOR is $60 per metric ton. And if you use, if direct capture is used, the tax credit goes up to $130. The numbers on the left are the tax credit before the Inflation Reduction Act was amended in 2022. So these are the amounts that were before this this bill, and the increment in tax is significant, and that really it created landslide of projects, because with this amount of credit, many projects had the opportunity to be with cash flow positive. So this amount of credit really helped finance those projects. So the tax credit eligibility, number one, the capture. So CO2 must be captured from an eligible industrial process, a power plant, or an other qualified source. The CO2 must be stored or sequestered in a qualified geological formation. This typically means a saline aquifer or an oil and gas reservoir. And also could be utilized, could be used in certain industrial processes, or it can be used as a EOR, like we explained here, but also can be converted in other products that also eligible. So what is the size of the price? So the credits available equal the amount of metric ton of CO2 captured times the applicable rate. And these credits are available for 12 years after facility is placed in service. And after that, after 2026, an inflation factor is applied. So, for example, if you have to have an idea how much is the size of this incentive. If you have a project that is storing 500,000 metric tons of CO2, capture and storing 500,000 metric tons of CO2 every year at a facility placed in service in 2025, you have either two things. Your project will be valued $360 million in credits if that CO2 was stored on a CO2 EOR project at $60 per ton of CO2. But if that same amount was used on for example, in this case, acid gas injection well, assuming that it qualifies for $85 per ton, then that project will be worth over $500 million in credits. And the same amount or the same credit amount will apply for a geological storage. So this just, you can have an idea of the amount and the magnitude of the credits. This is considerable, sizable incentive. And no wonder many companies jumped at the opportunity of using these credits to finance these projects, lower the carbon footprint, and reach their emission goals by their target date, and also optimize their current operations. So all of this to be able to go to the IRS and claim your 45Q tax credits, you have to quantify your CO2 stored, but also you need a third-party verification. The 45Q needs a independent third-party verification annually by a qualified engineer and geologist, and either for CO2 EOR or for utilization. It will need also life cycle analysis. California low carbon fuel standards also have different standards, and to be able to, let's say, claim the tax credits that they have, and also the project had to be verified by CARB and approved, and had to be an approved third party. So the regulation require a third party to verify the calculations of the actual amount of CO2 that was stored to be able to claim the tax credit for your projects. Okay, so this final remark, in our opinion, CO2 EOR is a win-win strategy for the beneficial use of industrial CO2 sourced. From the economic standpoint, CO2 EOR is a highly effective tool for revigorating oil production in mature fields. And also from the environmental standpoint, it represents a practical way to recycle and use CO2 while reducing the overall atmospheric CO2 emission. Similarly, by utilizing or using acid gas injection, companies can comply with the regulation and reduce their carbon footprint and continue their operation. Well-produced CO2 was previously viewed as a liability for oil and gas upstreams and midstream companies. The same volume of produced CO2 can now generate income using this credit and also improve the oil and gas project economics. So lastly, companies should prioritize the integration of carbon capture technologies as a core element of their business strategies to remain competitive and responsive to regulatory changes. And that is the end of my presentation. Thank you for your attention, and I'll be online for the Q&A. Thank you very much.